Hi, y'all. Man, I was looking at my watch. I thought it was 11. But what time is it really? My watch must be slow. 11:03. I guess that's not too bad. Landon's here. Whoa. Let me see your face, Landon.
Oh God.
Come on, commit. We don't care if your hair is not. If it's sticking up. It's actually better. There he is. Good. I just want to make sure you're alive in the world.
Yep, finally back.
You don't have to keep your camera on if you don't want. I just wanted to say hi.
You haven't shaved in a week and a half, so
Nice. How's everybody doing? Functional? Um, let's see. Do I or do you want to say anything about the test? I know Evald asked about question 5, which was a little bit messy. Can we talk about that after class, Evald? Can you stay after for 10 minutes? Okay.
Yeah, I can stay after. Yep.
Okay. Um, so I have really good news in the sense that where we're going now, and again, you may notice on the syllabus, if you kind of look at it, that we went from chapter 2 to chapter 4, and now we're going back to chapter 3. And that might sound really weird, but I did steal that from what they're doing at at OSU and at OIT with respect to how they're handling this book. And I think you'll see why today, because we don't really have to learn anything new now to get what we're getting today. And I've been hinting at this, but all we're really going to do now is just make sure stuff actually doesn't move. What we've been doing so far is finding the resultant force. And then we've just been saying, hey, there's the result. And a big part of your test pertained to that. And incidentally, with respect to your test, I would greatly encourage you to argue with me about that, like points. And also, I don't care if you missed 1 point, like make sure you know why. Maybe I told you on the test and it's no problem, but make sure you know why, because I want you to understand everything we're doing. Take your time, ask lots of questions. Let's see. So we seem to be in freeze mode here. I've been having some trouble lately. I'm afraid that everything is lagging behind really slowly. That worries me a lot. Are you seeing all blurry and weird looking right now? Okay. I've been having a lot of trouble with what I'm sharing screen-wise lately because it's lagging behind in my calculus class, and now it's really doing it here. This is question 2 on the test. Hey, there it came. It's the same exact question. On the test, though, I asked you to find the resultant force. Calculate the magnitude and the direction of the resultant force on the ring measured clockwise from the positive x-axis. And you did that by converting everything into x coordinates and y coordinates. You're okay, Landon. We're not. This is just join us. We'll figure that out later. But what I've done here is sort of add one more force to it that's not in the picture. And this is why I'm saying you actually don't really have to learn anything new. Does it make sense that your job as an engineer, as I've been saying from the start, is to make stuff not move? And so if I look at that ring right there, and let's just pretend that's one part of a bridge. There's all these things attached to it, and there's a train driving across it. So that's one joint on the bridge. Well, I need that not to move when all of those forces are acting on it. And so what you saw from the test is, well, no, there is a resultant force. Together, all of that is actually going somewhere. But does it make sense that if we're going to stop this, we've got to add kind of one more force to stop it? And that's kind of what I want to illustrate today. Oh man, I hope this works. So let's see. On the test, I'm just looking at this question on the test to see where the resultant went. Actually, I think I'm going to do this randomly. Oh, good. It's showing up quickly. So I just put force 4 on there. And now what I need, and with respect to this concept of equilibrium, equilibrium is code for I would really like the sum of the forces in X and the sum of the forces in Y to be equal to 0. If they're not equal to 0, then this thing is moving and the bridge falls down. Does that concept make sense? We learn nothing new. All we have to do is just make this not move. So in a sense, what we're doing is attaching another cable to this or another force. And I also want to introduce today, and we'll go into this a little bit more, but the concept of a free body diagram, often abbreviated as FBD. And these are huge and you need to draw these. I will be asking them for you. I will be asking them from you on the next test. I will be giving you points for them. Out of laziness, there's sort of times when you don't need them. But this already is a free body diagram. Does it make sense? Like there's no bridge, there's no train. All there is one joint on the and then there's 4 forces kind of pulling on it. Does that make sense? And so it's free body in the sense that you just look at something according to what forces are acting on it, and that's it. And those are arrows pointing at it or arrows pointing away from it and so forth. Okay, well, let's do this. So force 4, I'm going to put this at an angle of theta. And notice I don't really know where to put it. I'm just kind of sticking it on there. If you look at your last test, you could actually tell which way it's going to go. So let me see, I'll just mention this. Let's see, on the last test, it went kind of in that direction. It went like in this direction over here, if you remember, on the test. And so realistically, if you want to stop that, does it make sense you need another force going the other direction? And that is the concept of a couple moment. That's why you keep seeing that word come up and you're like, I don't understand what that's really talking about. Does it make sense? Those two forces are the same size going in opposite directions. They're parallel to each other. They're even lined up in this case, but that's what I'm going to have to do to stop this. And so the real answer to this question I know is over in the 4th quadrant. It's like over here somewhere. That's where it really is. But again, that's kind of cool that I don't have to kind of know that up front. So let's just do this. Again, it requires nothing new. This is what's so cool. So let's get the sum of the forces in X. By the way, some of you are really growing in your work, like as an engineer. Your work is getting it's clear, it's easy to read and follow. Remember, that's not so much for other people to look at, but just so that you don't make math mistakes. So I'm seeing progress in that. Good job. Okay, so I got force 1, force 2, force 3. I know what all those are, and so let's just get after it. So force 1 is 480. I'm doing this in the X direction, and I'm going to be kind of liberal about what I do with the angles. Like if that's 27 up there, then that means this is also 63. If that's 47, then this is 43. If that's 77, this is 13. I'm just not sure which angles I might want to use. So I'm just kind of putting those in there. So let's see, sum of the forces in X. I need the sum of the forces in X. So I'll take my force 1, which was 480, but to get its X component, I've got to multiply that by the cosine of 63 would work. I'm doing something wrong. I want you to think about what it is. And so there's a force. And then I got force 2, which is 365, but it's modified by the cosine of 47. Please interrupt if you're not tracking with anything that I'm saying here. I'm hoping you're a little faster at this process now, so that what I'm doing does make sense to you. Notice I'm leaving out the signs for a second. And then force 3 is 275. So it's 275, but modified by the cosine of 13. Do you understand what I just did there to save a little bit of time? If you use the angle against the x-axis every single time, then it's always cosine. So that's why I used 63, 47, and 13 for my angles. Now, because those angles are not measured from zero, remember we call this zero, I've got to supply the negatives myself. In other words, I can see force 1 is actually going left, so I'm supplying a negative sign there. I'm going to change the color of it just to make it stand out for you. It's actually left, and then force 2 is also left, whereas force 3 is actually right. And force 4 that I now need to add, because of where I drew it anyway, and remember, I don't even know if I drew it in the right location, that'd be force 4 times the cosine of theta. And that's going right, so it'd be positive. And so the important thing here is to come back and say, good for you, but the whole point of writing that all out, I got to make myself a little bit of space here, is to what's missing from my statement that I'm making room for right now? Read my mind. What's missing? Come on, what's missing?
Oh, set n equal to 0.
Bam. Equal to 0. That's all we're adding. That's all chapter 3 is that's different than anything you've done before. Equals 0. That's what equilibrium means. Equilibrium means stuff's not moving. Now, what's wrong with this equation? What do I not like about this equation? As an algebra student, as a math student, what do I not like?
You have 2 unknowns.
Good. 2 unknowns. A theta and a force 4. As an algebra student, and this is very important in this class, you need to think, if I've got 2 unknowns and I need to solve them, then I need 2 equations. Unfortunately for us, there's a sum of the forces in y equation that's going to allow us to answer this. So that's awesome. So note to myself and to you, blind assumption, force 4 is in the first quadrant. You can draw it anywhere you want. I drew it there because just looking at all the arrows, it looks like 2 are pulling left, 2 are pulling right. That looks like about where it would be. That might have been my guess, if you will.
Yeah, my first thought notation wise would be that I probably wouldn't even put the force 4 cosine theta. I'd probably just put the force 4 x component in there instead, and then worry about the angle after I've already got both the x and the y components.
Nice job. Does everybody understand what Landon said? You can totally do that. In other words, you can, instead of calling this force 4 cosine of theta, I could just call it force 4 of x. And then I would get force 4 of x, force 4 of y. And then you could use those 2 forces to figure out what the resultant, what force 4 is. Does that make sense? So absolutely. The only advantage to what I'm doing, and I would somewhat say it maybe even as a disadvantage, is I'm going to get them both. Like I'm going to get actually force 4, and I'm going to get the angle it's at kind of at the same side. Now, unfortunately, I'm going to have to solve 2 equations, 2 unknowns to do that. So I would again highlight what Landon just said, and like you're totally willing just to call that force 4 of x, and then you only have 1 equation, 1 unknown. Super glad you pointed that out. Okay, we're rolling. What about the sum of the forces in y? See, this is taking a lot of space, so I'm going to save a little more room this time. Sum of the forces in y. Well, notice I can go really fast here. The only difference with the one above it is it's still going to be 480, but this time it'll just be the sine of 63. And then I look at the picture and see that's going up, and so that'll be positive. And then I see force 2 is going down, so that'll be negative. So it'll still be 365 and 47, but it'll just be the sine of 47. And then force 3 also down, so it's negative. So it'll still be 275 and 13 degrees, but it's just going to be the sine of 13 degrees. Again, if you use one of the, you can use, I'm using pluses and minuses because I'm looking at the picture, but does it make sense if you actually labeled force 1 over here? I'm going to erase this, but if you measured it from 0, and that'd be 90 plus 27, if you called this 117 degrees, then the negatives would take care of themselves. Do you understand that? I could just say plus, 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 plus every single time. So if you're a person that likes automation, then change those angles to be measured from 0. And then you could just say plus, 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 plus every single time. There's a good argument for both. And then finally, again, I have force 4 visually, stupidly going up. And so that would be plus force 4 modified by the sine of theta. And this is also got to be equal to 0. So I have 2 equations, 2 unknowns. Which as much math as you've had, I hope you go, okay, good, I'm home free now. This isn't hard at all. But I am gonna walk us through that. So of course, all I have to do is type in all of that junk. I have to type in negative 480. I'm just giving you time to process. Cosine of 63 minus 365, cosine of 47 plus 275, cosine of 13. And when I do that, I get negative 198. So that means the force 4 of the cosine of theta minus 198. So I think I'll add it to the other side, 198.89. Again, stop me if I'm doing anything algebraically too quickly that you just don't feel good about. Or even if you just want to say, hold on, let me think about what you just said for a second. So I'm looking back at my calculator to make sure I typed in all the signs right, make sure every number that I think I just typed is actually in there. Now I'm going to hit second entry to retype this whole thing, and all I'm going to do is go back and change the signs and change everything to sine. 365 is still negative, but it's the sine of 47. 480 is now positive, and it's the sine of 43. So I got 98.87 plus force 4 sine of theta equals 0. So that would be force 4 sine of theta equals negative, because I'm going to subtract it to the other side. Again, I don't know how far to carry this out. I'm just going to choose 2 places. What would you do to solve it from there? I got 2 equations, 2 unknowns. What should I do to solve that? What would you do? How do I get rid of one of them? I got to put them together in some way to get rid of one of them. This is
You could
not,
solve for the F4 in one of the equations and then substitute that into the other one.
yeah, it's a little easier to solve for F4 than it is for theta. And so if I took this first equation and I solved it for F4, that would be F4 equals 198.89 divided by the cosine of theta, which then of course I could sort of deposit into this location. So now I have 198.89 divided by the cosine of theta times the sine of theta equals negative 98.88. That's not so great unless you're pretty good at algebra. How are you going to solve that for theta? You get really lucky here. What is another way to write when I multiply this out? Does it make sense algebraically to solve for theta? You need there to be only one theta. What trig identity is hopefully in your mind, telling you how to get out of this mess. Don't make me call your 112 teacher and change your grade to a D.
Tangent theta, because sine theta over cosine theta is tangent.
Yeah. Fortunately, sine over cosine is tangent. That accomplished something wonderful for us because now I only have one theta. And now I can divide by 198. 198.88 divided by 198.89. I got 0.49. Tangent of theta is approximately 0.497. And then I'm going to take the inverse tangent. Theta is the inverse tangent of that number. And that number is negative, which I failed to write down. Negative 0.497. So second tangent, negative 0.497. I got about negative 26 degrees. Theta is approximately negative 26 degrees. What does that tell me? That tells me in my picture that I guessed wrong. I would have wanted theta to be like 20 degrees or, I mean, my guess doesn't make guess look like about 30. And it's saying, nope, it's actually based on your drawing, it's actually negative. Oh, okay. Cool. And now that I know that, I can go back to either of these two equations and solve for the actual force 4. So I'm just going to say pick one. So I'm going to pick the positive one. So force 4 times the cosine of theta was supposed to equal 198.89. And if I throw that in there, and the real answer to that is, maybe I'll write it out one more decimal place, negative 26.42 or even 43. Maybe I should just, be a little more accurate. So if I throw that in there and I take 198.98 and 89, and I divide by the cosine of that negative 26, negative 26.43, then I get 222. And I paid no attention to this till now, but what were these forces? Oh, newtons. If your test is in front of you, those two answers should not surprise you because they're exactly the opposite of what you got on your test question. I think everybody got that one right. They're the exact opposite of what your test resultant was. So does it make sense that you could have just taken your test question and then just turned it around the other direction and it's the same exact force and that would have accomplished the same thing? This is just a little bit more of a formal, kind of a natural way to do it, I guess you could say. That's what this section's about. So basically this is telling me then if I went back up here and sort of attached a cable over here that was capable of pulling back, that's strong enough to hold 222 newtons without snapping in half, then that would achieve equilibrium while the train drives across, causing all these forces. Does that logic make sense? It's not really new. I want to warn you about a question in your assignment. Like this equation solving business that I had just ended up doing right there, that can sometimes be really nasty. And I'm warning you right now, question 23 in your assignment is a difficult equation to solve. I have a note to myself that says you actually have to solve it by graphing. Like you can get equations that are really hard to solve. It's neat when you can solve it algebraically like we just did, wonderful. But you're led to the assumption because of all the math you've taken, because nobody ever gives you a problem you can't do in a math class. that all equations can be solved. All equations cannot be solved. Like sometimes you have to rely on a graph. I just want to quickly, I'll use Desmos. Let's see, I'm trying to remember this. So force 4, I'm just going to call that X. And then it was cosine of theta, which I'm just going to call Y. And that was equal to 198.98, I think. You might have written that down, so tell me if I got that wrong. And then it was X times the sine of Y, or force of 4 times the sine of theta. And that equaled negative something or other. I can't remember. Negative 89, negative 98.88. And this one up here was not 9.8, it was 8.9. So if I graph these two equations, now I'm going to switch to degree mode. What do you notice about the coordinates of that point? Isn't that cool? Like this is what an engineer would do. I mean, it's wonderful to do things by hand. You're probably enough of a mathematician to make it this far that you take some pride in being able to figure things out by hand. But remember, you can't afford to get things wrong as an engineer. You got to get them right. And so I just saved a bunch of time and guaranteed I didn't screw up there. Isn't that kind of cool? And this particular question I showed you in Desmos because you can't even stick this in your graphing calculator. Well, not easily. You can if you resolve it for X equals 198 divided by the cosine of Y, and then maybe switch the letters so it looks like it's Y. In other words, I used them backwards, like I used X and Y backwards. So if you typed Y equals 198 divided by the cosine of X, like your graphic calculator only works if you solve it for Y. Like it has to be Y equals and then junk after it. But you can't always solve equations for Y that easy. This time you can solve these for X without too much trouble. So take advantage of that. Engineers don't get any extra credit for doing all the algebra. This is an engineering class, not an algebra class. For the most part, I don't have any problem with you graphing stuff like this. Since we're taking notes on this and posting it, I might as well just stick this in the notes.
I kind of feel almost obligated to ask. Can you avoid all the trouble of, well, in this case, not trying to solve it or plugging it into a graphing utility by breaking it into just separate components and working from there?
Yeah. I mean, there is more than one way to do this. What I'm showing you is kind of just a systematic way. If you add up all the forces in X, all the forces in Y, all the forces in Z, we just need them to add up to 0. If you go about that in any kind of a creative way, because it makes more sense to you, great. Cool. So that's an introduction to what really chapter 3 is talking about, the concept of equilibrium. And so now let's take this to another level. And let's get a pulley involved. So there's two things that get added to this section. In one respect, chapter 3 is nothing new. You need to know nothing new. But in another respect, there are things involved sometimes that you got to account for, like a pulley or a spring. Those are two things. And you've had some physics to get into this class, so both pulleys and springs should not be entirely new to you. But this is a pretty hard question here, question number 11, for a few reasons. But the first thing we want to draw here, and it says nothing about this, is our free body diagram. Free body diagram. What does that mean? Well, see, notice this is not a free body. Like I see the ropes attached to a weight. I see the pulley there. I see the ceiling, and there's something up there. And so a free body diagram is where you reduce it to kind of a dot, you know, whatever it is you're looking at. And in this case, all three of those cables are pulling at A. And so the free body diagram makes the most sense if I really just draw this. If I say this is point A, and there's a force over here, a force over here, and a force over there. Now, are there other places I could draw a free body diagram? Absolutely. You could draw it at B. But up at B, you would have the force of the ceiling, which is pulling back, and the force of the cable, which is pulling in this direction. And we'll get to this later, but because of how that's attached up there, it isn't just a vertical force. It also is providing a horizontal force because of the way that's attached up there. I don't know if that makes sense to you. We'll get to that later, but so there, you can draw a free body diagram in any particular location where there's just a bunch of forces happening on things. But in this case, because they're asking me about, you know, A, B over here, they're asking me about, you know, this cord and this cord and this cord, all of them are attached at A. So A makes sense to be the place to draw the free body diagram. Do you see that? So a free body diagram just simplifies things. It gets rid of pulleys and ceilings and attachments and weights and all that stuff. And you just put arrows, which are vectors with forces on them. Now, pulleys, easy. What do you know about a pulley? If you have a pulley and you're pulling over here, how hard do you have to pull on that to lift that box? Well,
50 pounds. It's the same.
Yeah, assuming an ideal pulley.
Yeah, if it's.
What does ideal mean, since you brought that up?
Let's see. Frictionless, not moving.
Yeah, frictionless. Nothing is lost. And now there is things lost in a pulley. So realistically, you'd have to pull a hair harder than that because some of your force is wasted in the pulley. But in an ideal or smooth, you'll see the word smooth in some of your assignments. In a smooth pulley, those forces are going to be equalized. That's kind of the key. And by the way, like, this doesn't mean it has to stop. Like, if the cable is pulling at a constant speed, they can both still be 50. But the point is, cables equalize. You can't have, it's impossible to have on a cable 150 over here and 50 on the other one. Do you understand that? Because that tension is, just because the cable is turned around a corner, that tension's the same. If you're playing tug of war and you got two people on the end of a rope and they're both pulling at 100, then this thing is not going to move. If the right people on this side over here are pulling at 100 and these people pull at 50, then it's moving. Like, the cable is going to equalize those forces. And so that's what's going on with pulleys. That's the simple answer to it. So they sort of equal on, I'll just say, all locations, just to keep it simple. And you don't have to just have one pulley. You could go through numerous pulleys and the same thing would be true. So that means whatever, I have to kind of add that to my free body diagram. I can't say force 1 and force 2, like those are different. Do you see what I'm saying? They're not different. It's force 1 and force 1. So that's actually kind of good. Now in our last problem, there were 4 different forces and they were all different, right? So that's force 1 and force 1. And then I guess this up here would be force 2 or something like that. Notice they don't tell me any of them, otherwise I would have put them in there. So this is kind of a cool problem because they're basically saying we got this block down there that has some weight, but they don't tell us what that weight is. But they do tell us your cable's going to snap if it's more than 80. Does that make sense? That's what they tell us. So whatever box you hang on there, if you end up with any of those forces, force 1 or force 2, more than 80, then snap, doesn't work. Would you agree that, well, which one of these is going to be the biggest? Is force 1 or force 2 bigger? Can you tell from the free body diagram from the picture?
Yeah, should be force 2, right?
Yeah, why do you say that?
Because it has to support at least both force ones pulling
Exactly.
on.
And they're pulling in the opposite direction. Do you also agree conceptually that if I said, okay, well, these are 50, do you agree this is not 100? Why is it not 100?
They're moving some in the opposite direction, so they're giving some vertically. It's
Yeah.
only the forces in line with that needs to be accounted for.
They'd have to be lined up with that for that to be the case. If both those red cables were pulling straight opposite of force 2, then it would be 100. But it's wasted. So therefore, this is not 100. This might be more like, I don't know, like 90 or something like that. Does that make sense? I said not equal. Might be more like 90. Do you see what I'm saying? I'm just trying to make sense. That's all I'm trying to do here. And so if this is going to break, does it make sense it's going to break here? It's going to break up there. So the point is, like, what do I do with the 80? If I reason about this a little bit, I don't want to put the 80 down here because then force 2 is going to obviously be more than 80 and then it's going to snap. So I can put 80 in this picture, but I really want to put it up here. And so what that tells me is these forces down there are going to be less. Does that make sense? Maybe 50 or something like that. You see the logic in that? Now, do you have to know that? No, very possibly I could just set up a system of equations with force 1 and force 2 and have 2 equations, 2 unknowns, and just solve it. And maybe that would work and I wouldn't even have to kind of reason this out. But in this case, I can. So I think it's just good to learn how to think. So, all right. I've got my free body diagram drawn. I've got forces every place that I know them. What's my free body diagram missing? It is missing something. What's it missing?
Force of the actual weight.
No, I got that on there.
Okay. No, yeah, it's
Because I got force 1 on there. That's on there. I don't know what it is, but I got something representing it, and it's a
Angles?
letter.
You missing angles?
Yeah, it'd be nice to have the angles. Now, again, this is not something I'm going to nitpick because, the angles are in the other picture over there. And then notice the angles measured at the top. Do you understand from your geometry knowledge that that would also be the same if I put it right here? If you have a parallel lines and a line cuts through it like this, that angle will be the same as that angle. Is that the only place I could put it? No, I could do what I did a minute ago and say, well, that would make a right triangle. And if that angle up there at the peak was 20, then wouldn't this be 70? But again, you're going to have to just get creative with angles. Reason it out, go slow, reason about, use your math skills, draw a good picture. And then the other one, unfortunately, I don't even know. Like they told me, you don't know that one. And so this is kind of a cool problem because they're basically saying, hey, I've got this system attached to the ceiling, and you can imagine somebody building this and they're going to use it to lift things. And so the question is, like, what's the load limit? Based on the rope you chose, what's the load limit? You better not pull more than this. And remember, this isn't just some dude hoisting. Like this is a bridge being lifted by a crane. When you get this wrong, like the whole things fall down in a large way. This isn't just like some guy dropped the box like it looks like in physics. So now my free body diagram's got everything in it, and now I'm free to just go do what we do, which is to say, well, let's add up all the forces in X and make sure they're equal to 0. Let's see. Well, there's that 80 up there. That'd be 80 modified by what? It's not 80 because of the 20 degrees. Is it 80 sine of 20 or 80 cosine of 20? How quick?
Sine of 20, I think.
You're right, because sine of 20 is opposite of 20, which would be the horizontal. And now, and maybe you see that that's negative. As I said, if I put the 70-degree angle in, it would have been the cosine of 70. Maybe that's easier for you to see if you do it against the horizontal axis, like I said before. Great. Lots of ways to do that. So that's pulling left, and then force 1 is pulling right. But it's also modified by that angle. And just like the other one, if I wanted the horizontal component, that's opposite of the angle, so it'd be sine. So the sine of theta. And notice that force 1 makes no contribution in the X. There's two F1s here, but only one of them actually makes a contribution. Again, bummer, because I got two unknowns here. So I'm not happy. It would have been awesome if there was only one unknown. As Landon said, maybe I could, do this differently so I didn't have to worry about it that way. But it's just kind of cool to write this down. If you just kind of almost, I don't know if the word is mindless, but if you just kind of say, hey, I'm just going to write down some of the forces in X equals 0, some of the forces in Y equals 0, and then just let math take over to answer it. Is there an easier way? Well, sometimes, but write it down. So, two unknowns. Two unknowns again. But we have much hope because we have two equations. And so let's get the sum of the forces in Y, which is also going to be equal to 0. Well, force 2 is pulling up this time, so that'd be 80, and it'd be the cosine of 20. That's pulling up. Force 1 is pulling straight down, this force 1, and so I don't have to modify that at all. It's straight down, and it's negative. And then the other force 1 is also down, but it's modified by not the sine of 20 this time, but the cosine. I'm sorry, not the sine of theta, but the cosine of theta this time. And so, okay, cool. At least I have two equations, two unknowns. Sweet. Two equations, two unknowns. And so again, I'm in the same place I was before. Can I do this algebraically? Should I just cheat and type it into Desmos? Based on the picture, I'm expecting, theta to be like, I don't know, 40 degrees, whatever. And force 1, I know is less than 80, so maybe it's 50 or something like that. So I don't know, does that look easy to solve? I mean, again, I can see the same thing is happening last time, and this is pretty messy. So I find myself thinking, I think I'm going to cheat. Where's my phone? as I said, the mathematician in you that you would have to even get this far, the mathematician in you should kind of take exception to this. So I'm just taking a picture of this because I'm about to lose my work when I switch to Desmos. So let's see, I have almost something similar to last time. The first equation was F times the sine of theta equals plus, and I'm gonna go ahead and write out exactly what I have this time. You don't have to solve it. It's just for that F1 times the sine of theta, I had negative 80 sine of 20. Like you could bust out your calculator and figure out what that is, but that's just another step. So why not leave it out? Plus that equals 0. Just type what it says. And then the other one was 80 cosine of 20 plus, I'm sorry, minus F1. I was calling F the X. So minus X and then minus X cosine of theta. And that all needed to add up and be 0. So you're seeing the equilibrium equations. This is very wonderful. So isn't that typed correctly? I don't know if you wrote that down. You don't need to, but I'm double checking to make sure I wrote it down right. 80 cosine of 20 minus X cosine of theta. I did not write it down. It's a good thing I did check because that 0 didn't show up. Negative 80 sine of 20 plus X sine of, okay, good. Now all I gotta do is go look at the graph and see where they cross. Hello. Right there. So the X for me was force 1. So the force is 42 pounds on those two ropes and the angle was exactly at 40 degrees. That makes me think that this is kind of a canned problem, that it came out exactly 40 degrees, don't you think?
Looking at it intuitively, it kind of makes sense though, because just imagining how the rope holding the pulley would have to be pulled. It
Right.
kind of just makes sense. It would just be, like twice the angle that the pulley is set off at.
Twice.
Or if you just set, the way I like to look at it is if you just set your axis along the F2 vector,
Mm-hmm.
then it should be symmetrical on both sides.
I like what you're saying. So the possibility of the symmetry involved in this sometimes can be like, oh yeah, I should have thought of that, or whatever. I mean, there can be things that you can do to save time, but so I can say that force 1 must equal 42 point, well, your book is going to say 42.56. It's going to say 42.6. And that was in pounds. You see how powerful this is? Like even when you aren't just given all the forces, but and I guess I hope you see this as a fairly realistic question, a little more realistic, because as an engineer, you don't just say, hey, this weighs, 1,000 pounds. How much tension does that put on the rope? Because that might break the rope. You kind of go the other way and you say, well, how strong is the rope that's there? And then you work backwards to tell somebody, well, this is your load limit. That like 42 pounds, that would be good then for you to come back here if this was, a part of a ship or something like that, and say this has a 42-pound load limit. Don't use it over that. And that would not be a very good factor of safety, would it? Was that what it would say, 42 pounds? No, it's probably going to say Well, if there were people underneath it, it's double. So it's going to say 20-pound load limit or something like that. But if you can calculate 42.6, then you can decide what to do from there. What do you think? You feeling good? Tracking? I want to point one thing out. In this case, it just kind of happened automatically. But notice all my arrows are drawing outward. They're drawing outward. Because these arrows were drawn outward, does it make sense I was assuming tension? And of course, you can by logic in this case. I mean, you can tell because they're ropes, but ropes don't work in compression, right? A rope is not going to keep something in the air. If you put a rope under it, it's just going to fold into the rope. Ropes are good in tension. But this next question we're going to look at, not all shapes, are made entirely of cables. So it's the same problem, but we're just going to go 3D. And their drawing is really good. What do you notice if you look carefully at the drawing, at the different members that are attached? And notice it's the same thing we just did, except for now the box is attached with something that's three-dimensional. But again, you probably can tell by logic, just looking at it, if you put a bunch of weight in that box, what are A, B, and AC? What are those doing? Are they being pulled in tension, like they might snap in two, or are they being crushed in tension, which means compression, which means they might buckle and break? You can tell by looking. Maybe it's a little less obvious about AD. What's happening to AD if you put too much weight on that? Is AD going to be crushed in compression, or is it going to be snapped in two in tension? Can you tell by looking? And I actually don't know if you can tell. I'm older than you, have built a lot of things, so I can tell. But
I'm guessing compression for the AD.
yeah, your instinct is right. Now I want to show you something cool about this, though. In this case, they even drew that. Can you tell that A, B, and AC are cables just by the way they drew it? Whereas AD is more like a pipe or something. Because AD is getting compressed. And so you can't use a cable there. It's got to be something solid, pipe or something like that. Whereas AB and AC are getting pulled. And so then you could use a cable in that situation. So maybe you can see by inspection that the top two black ones are in tension and the bottom one's in compression. So if the two forces are pulling in this way, that's tension. If the two forces are pushing in together, that's compression. That's the other thing we're adding in this section is now we're talking about not just what's the force. You may remember on your first test question, how much force is on this member? And the answer was, 120 or whatever, but you didn't say tension or compression. But in the real world, you got to know that. Like, you can't not know that. A pipe works in both situations, but a cable only works in tension, for instance. Cables are a lot cheaper, and they're also flexible, which is really cool. Notice they even told us, determine the tension developed in cables A, B, and AC, and the force developed along the strut, AD, for equilibrium of, thank God, a 400-pound crate. So they're telling us this thing weighs 400 pounds. Or, it's you're designing this. And so, and again, I like to picture this as just something somebody designed to lift boxes off of a ship. So it reaches out over the water, and now you can just lower the crane, pick something up, haul it up, spin it around. And this is weird because in that drawing, you can't turn it. Like, you can just lift it up, but you can't turn and put it anywhere. What does your free body diagram look like here? Free body diagram. How many free body diagrams are there? I found this confusing when I was first learning this. Well, there's a ton of them. Every place there's a connection, there's a free body diagram. You could draw one here. And by the way, an engineer needs to. Even if you make sure the black cable here is strong enough, could it rip out of the wall? The cable didn't break, but it tore out of the wall. You need a free body diagram at C to know how much force is on. And notice C doesn't know there's a box. C knows there's a cable attached to it, and it knows it's attached to the wall. That's all it knows. And so we would draw C as a dot and some force arrows off of it. Same at B, same at D. But the most important one for us is A because it's attached to everything. Does that make sense? So we want the free body diagram at A. And I'm going to do something that, I don't know, might surprise you a little bit. So A has got 400 pulling down. It's got this strut coming back in this direction. I'm just trying to eyeball it to look reasonably similar to what I see over there.
Jordan Gardner.
And this other is over here. How do I draw arrows on those? Like, do I draw the arrow on the left or on the right? And I want to give you some important advice about that. You cannot always reason this out. If you look at a bridge that has we'll get to this, trusses later on that have a complicated lattice work of bars in them, you cannot reason out which ones are in tension or which ones are in compression. It's very surprising sometimes. So it's really helpful if you assume tension, even if, like we said a minute ago, you can tell AD is in compression. It's actually helpful if you just assume tension every single time, which means arrows always point out. This will save your butt. Now, what's going to happen is any answer, any force that comes out positive means you got it right. It's in tension. If it comes out negative, it means it's in compression. That way it's just systematic and you don't even have to think about it. Now, if you came back here and said, well, actually, I know this arrowhead goes this way, and I'll do the problem with the arrowhead going that way because that's under compression. Great, that works, and you'll get a positive answer because you're right, it's under compression. But it's just dangerous. Do you see what I'm saying? It's dangerous if you kind of get it wrong. And in this case, you might get it, but as I said, in trusses, you won't. So just assume tension, it'll be really easy. Well, I don't know about you, but this feels really complicated because, I mean, I got forces going everywhere. And then this is also 3D, right? So I'm going to call, because this is D down here, I'm going to say this is the force in D, and this is the force in C, and this is the force in B. And so basically what they're asking me is, you know, what are all of those? And can you appreciate this is what engineers do right here? I mean, this is the bottom end of it. Because if you can calculate all these forces, then you can put the right size members in there, the right size pipes and cables and stuff. You got to come up with these numbers. Now, what are we going to do for equilibrium? For equilibrium, we need the sum of the forces in X and the sum of the forces in Y, and in this case, because it's 3D, the sum of the forces in Z to all be 0, meaning they're not moving. This word equilibrium needs to jump off the page at you. So the 400-pound weight is causing the problem, and the other members are going to have to react to that. So let's go get it. Do you notice all the dimensions on the original drawing are kind of the key here? Now again, do you see why? Do you really need to draw a free body diagram here? I didn't really do anything but just redraw the picture that was over there, right? I'm going to give you a second to think about that. I'm teaching right now, so
Talk to you in a bit.
I'll call you
Okay.
back. So do you need to learn anything new here? The answer is no. You've already done this, but we have to convert force D. We have to write down what's its X, Y, and Z components. You've done this before. So this isn't really new. Just going to give you a second to think about that. Can you stare at those dimensions? I'm going to get my crap together and get all organized here. So I've got to break force B into its X, Y, Z components. And based on all of these directions, and notice again, it's very important to understand the arrowhead is pointing back at the wall. So the force is going from A to B. Uh-oh, my machine is freezing. Going from A to B. So I see dimension wise, let's see, from A to get to B. What am I doing? I'm going -2 in the X direction. Do you agree with that? And what am I doing in the Y direction?
-6.
Yeah, backwards 6. What am I doing in the Z direction? It's a little more complicated.
+4.
It's not +4. That's very tempting.
Oh, yeah, I see it. It's +1/2.
Yeah, notice it's, let's see, this is 2.5 off the ground. And this one is 4 off the ground. So it's those two different. It's 1.5. Do you agree with that? I'm saying that like I'm questioning my own thinking there. Do you see how deceptive things are in 3D? Because yeah, Landon's first thought was also mine, which is, oh yeah, that's 4 feet up. So you got to be really careful. So it's already 2.5 feet in the air. Now it's going up to 4. So that's actually 1.5. So you could say from A to B, notice the way I drew that, A to B with an arrowhead, it's going, we said -2 feet and -6 feet and positive 1.5 feet. That's a cool way to write that down. More of you, probably because of what you learned in physics, are writing it this way from what I'm looking at on tests. Do you like one of those better than the other? I mean, the point is just make a list. Doesn't matter how you write it. Great. So if I use the Pythagorean theorem, that is how I get the, so I'm going to write the magnitude of AB. Notice I didn't put arrows on that. The magnitude of AB, Pythagorean theorem, 2 squared plus 6 squared plus 1.5 squared is 42.25, square rooted 6.5. Pythag. I'm assuming you sort of feel okay about that. So what does that mean force B actually is? Force B then could be called -2 divided by 6.5 and -6 divided by 6.5 and 1.5 divided by 6.5. All multiplied by force B. Let's see, how do I say that? Do you agree that doesn't make sense? You can't say force B equals all of this multiplied by force B. How do I write that? It seems weird to say that.
Magnitude, maybe?
Yeah, magnitude. Yeah, that's
Yeah, you could put an arrow over the first force B. That would show that it's a vector.
An arrow. Yeah, that would do it. I could put an arrow right here, right, and say that's a vector. Whereas force B is a number. Do you see the difference between a number and a vector? So force B is a magnitude, force B is a vector. So maybe we need to start being a little more careful about that. Like this is nothing new, but it's pretty darn complicated in 3 dimensions, isn't it? Cool. Now I just need to repeat this for force C and force D. So force C, and maybe I'll go back and even put a magnitude over that one, force C. So from A to C, what is my dimensions in feet? How far, what am I doing to get from A to C? Well, I'm going 2 feet in the positive X direction. Again, 6 feet in the Y direction, and up 2.5 feet, but then up 5.5 feet. So it's actually 3 feet up. You agree with that? So it's 2, -6, and 3. +2, -6, and 3 feet. And if I put that into the Pythagorean theorem, I get 49. So AC, the square root of 49 is actually 7. So somebody put some thought into this. AC is actually 7 feet. The distance AC is actually 7 feet. Just like before, the distance was 6.5 feet. And so then I could say that force C's vector split into its X and Y components would be in this ratio: 2/7 X, -6/7 Y, and 3/7 Z. And if I multiply that by force C's magnitude, actually what force C is as a number, that gives me its X, Y, Z components. And again, you see where we're going with this, I hope, because we got to add up all the forces in X and set them equal to 0. We got to add up all the forces in Y and set them equal to 0. So I have to have all these components. Lastly, what's force D? Well, from A to D, again, from A to D, not D to A. What's different about that? Well, it's still 6 feet out, like all of them were. They're all 6 feet out in the Y direction. What is it in the X direction? It's very hard to see. Like, you got to really be careful.
I think it's 0, right?
Yeah, it's right lined up. A and D are lined up in the X axis. So it's 0 in the X direction. And then it's actually down 2.5. It's aiming down from A to D. It's going down 2.5. So I'm getting 0 in the X, -6 in the Y, and down 2.5. So if I Pythagorean theorem 6 squared plus 2.5 squared, I wonder if they made this work out nice. Oh, they did. It comes out 6.5 again. So AD, the magnitude is 6.5 feet. So then I can say, great, that means force D as a vector is equal to 0/7. I guess I'll write for 0, 6.5. Just to be consistent. -6 over 6.5 is its proportion, that's Y, and -2.5 over 6.5 is its proportion in Z. So if I multiply that by whatever force D is, then I'll have X direction, Y direction, Z direction. Now, you can convert these ratios like 3/7 to decimals. You could clean them up like 2.5 over 6.5. If I multiply the top and the bottom, that'd be 5 over 13. You can do create whatever you want with that. I'm just going to leave them alone just so you can see it. So does it make sense? I'm ready now to do all of the sum of my forces. I can say the sum of the forces in X then are, and I'm just going back and looking at these one at a time. -2 over 6.5 force B. And then I'm looking at this one plus 2/7 multiplied by force C. Looking at this one plus nothing. I'll go ahead and write nothing there. Nothing times force D has got to be 0 if these aren't moving, if I want equilibrium. Some of the forces in Y. What's going on at Y? Well, again, I'm just going back and looking at all those. -6 over 6.5 times the force of B minus 6/7 times the force of C minus 6 over 6.5 force of D. Again, that would look a lot nicer if I multiplied top and bottom by 2 and wrote 12/13. It would look a lot nicer.
Wouldn't the 2/7 FC in the force of X, wouldn't that be negative?
Did I screw it up?
Because we're going -2 in the. Oh no, you're right. It's +2. Yeah, no, I think I got it wrong. Okay.
It'd be easy to screw up. So I wrote positive 2/7 and I was trusting what I wrote. And you
I
should
think you did.
understand, like with this much of a problem, you're going to probably get one of those signs wrong. And it'll make everything not just negative, but totally screwed up. So wouldn't surprise me at all if I actually made a mistake. Force of Z. I see 1.5 over 6.5 positive. That's force B's X component. Force C's Z component. Force C's Z component is 3/7, and it seems to be positive. And force D's Z component is negative. And that also all needs to add up to 0. What do you see algebraically that you like here? Sweet. What's sweet about that?
Three equations, 3 unknowns.
3 equations, 3 unknowns. How do you solve that? That's not good. How do you solve that?
Yeah, you have to. It's complicated, or you can use matrices to do it.
Yes. We want to do this using matrix algebra. You could graph this, but that's a 3D graph. You probably never graphed anything in 3D. If you took Calc 4, you did, but I don't think you did because I would have. Ben did. Evel did. Both you guys did. So if you could draw a 3D graph, they would all hit each other at one XYZ point. But let's go to the graphing calculator for this, and we'll just have time for this, and then we'll be done. We didn't have time to talk about springs, and so whatever spring question is in your assignment is going to cause you some problems. I will maybe say something quickly about it if we're not too far out of time. But matrix algebra is cool, and you don't need to know, if you take Math 261, you'll learn more about the theory of this. Maybe you already did, but I'm going to go second matrix. And what size is my matrix? I have 3 equations, 3 unknowns. What size is my matrix? I'm going to edit a matrix. My matrix is 3 rows, 4 columns. It's a 3 by 4 matrix. 3 by 4 matrix. Notice in the window here, you can actually see all those numbers. There's the X row, there's the Y row, there's the Z row, and then off to the side over here, those little lines saying, hey, there's more stuff over there. I'm going to arrow over there. There's the equals. In our case, they're all equal 0. So those zeros are already in place. So I'm just going to start typing this in now. So -2 divided by 6.5. That was my first x. I hit enter and it moves over like a typewriter to the next line. And so the next one, the y coordinate of the first force was 2/7. And then the z coordinate was 0. Enter. Now I'm over at the last number. I'm at the equal sign, equals 0. Hit enter and it returns to the next line, just like typing does. And then it's -6 divided by 6.5. Notice it's turning those into decimals. And then -6 divided by 7. And, you know, again, I'm probably going to miss one. I'm probably going to type something wrong here. And then -6 divided by 6.5. And then equals 0. Enter. Now I'm down on the z forces. These are the z forces. 1.5 over 6.5, which is really 3 over 13. That'd be easier to type 3 over 13, wouldn't it? Should probably be doing that. And then it was 3 over 7. And then it was -2.5 over 6.5. And lastly, equals 0. Cool. All my numbers are in the matrix. So you're seeing exactly what was on my screen, just listed in the matrix. So
Would
now
we
you
have-
say, go ahead, what did I do wrong?
Sorry, I was just saying, will we have 400 also involved for the z forces?
What did I forget? 400. Where does 400 go?
Be yeah, I think -400 in z, and then you could add it over to be positive.
Good. I need to show you that because that was important. And that's easy to miss. And I'm glad I missed it just because it kind of helps you realize that. You get all distracted by, you know, the hard part of what you're doing. And then, but yeah, that z force, that 400 is in there. And so what I should have done that I'll add in now is, and I'll add it in red here, is say -400. That should have been stuck in there, shouldn't it? And so, as Ben said out loud, if that didn't make sense to you, that can't stay there because the first column are the B forces, the second is the C, the third is the D, and then the equal sign. So I got to add that 400 to the other side. Thank you for catching that. So back here then, I've got to type in 400. Notice down here on the bottom, 3,4. That's the third row down in the fourth column over, because sometimes there's so many numbers you can't even see them all. So now that that's done, I say second quit and second go back to matrix. And I see my 3x4 matrix there. I don't want to edit it. I want to do math to it this time. And if you arrow down to RREF, reduced row echelon form, which means nothing to you if you haven't had algebra, haven't had Math 261 linear algebra, reduced row echelon form. And now it's saying, what do you want to do that to? So I got to say matrix A because I had two of them in my calculator. Second matrix. Again, you can arrow around to whatever one you want. I want matrix A. And it says, okay, there you go. Can you read what that says though? Remember what the first row was? This was all the force B's, right? Force B, force B, force B, force C, force C, force C, force D, force D, force D. So what is this top row saying? Force B, one force B plus no force C's plus no force D's is 273. Oh, force one is 273. You see how that's, you see what row echelon form is actually doing? Row echelon form is kind of code for a whole bunch of zeros with ones in a diagonal. So I'm going to write that down and then I'll switch back to the other screen. What do you notice about the signs that doesn't surprise you? Remember, we assumed everything was in tension. But based on logic, we said it really looks like this is in tension, this is in tension, and that's in compression. Again, maybe you have that logic from your life on Earth. Because we assumed tension and we got positive numbers for B and C, then that means we were right. Those are in tension. But because we assumed tension, we got the force D, we actually got that negative, which means that's not tension, that's compression. So we weren't surprised it was negative, I guess is what I'm saying. The other thing that I'm kind of surprised about is notice D has got to work way harder, like twice as hard as B. That's the kind of thing you got to know as an engineer. Like that's got to be a lot stronger. So you actually know what it's going to take to create equilibrium now. Those three members are going to have to be capable of holding these numbers of pounds, or you're not going to have equilibrium. Something breaks and down goes the system. So the way you ought to answer this in this section, and we'll be done, is you should say this is 274 pounds of tension. You should say this is 295 pounds of tension. And this is 547 pounds of compression. And as I said, tension, you could use cables if you want for those, but compression, you're gonna have to use a pipe or something solid that doesn't want to bend. Can you do this?
So just thinking about it, when it comes to compression, I guess just looking at materials generally, I was thinking the failure mode of compression where it kind of just bends off. Would that mean that we'd have to worry about potentially kind of what directions are going into the compression in terms of how it could potentially fail? Or
Yeah, I understand what you're saying. Ultimately, compression is only acting along the axis. And if you push hard enough, if I push hard enough on this pen, the pen's not going to crush. It's actually going to bow outwards. Does that make sense?
Mm-hmm.
So one of the things that's interesting about compression is it depends on how long that pipe is, because it's not enough just to say, oh, here's a pipe that'll do. Because if it's really long, that's part of it too. So yeah, there's and one of the things you'll take spring term is strength of materials, and that's part of what you talk about. And there's like, well, what kind of materials could I use that won't compress 547 pounds? How long can it be? And what kind of materials are less flexible? Because it's really an issue of it bending out more than it just actually crushing. So that's a really good question. Cool. So I guess on Tuesday, like you may not be able to do the spring related questions. Read about it and see if you can, but I always like to be able to talk about everything, but this happens every week in this class. There's always something we can't get to. I have one more example I want to do and we just don't have time for it. If this was a 2-hour class, it'd be perfect. I will briefly at least show you its picture. This is the other question I wanted to do. So notice that's not 3-dimensional. But in this case, there's a spring on DB, which means when you put weight on it, that spring is going to pull out a little bit. Does that make sense? So this question gets it, well, how much is that going to pull? Like this has got stretch built into it, so it doesn't just snap the cable. And it turns out for a spring, I'm not going to post this in the notes, but the force on a spring is proportional to the distance that it stretches. And if you think about it, it makes sense in the sense that if I double the force, then it'll double how long the spring extends, if you will. And you might have seen that in physics. And then it's that K, that's the constant that relates them. It doesn't mean the force is the same as the length. That doesn't make sense. But it means they're proportionate. If you double the length, you're going to have to double the force to pull it that hard. And so the K is the spring constant. And notice its units are newtons per meter, because if you took K in newtons per meter and you multiplied it by X, which is a length in meters, then those meters would cancel and you'd get newtons, and that's force. And so spring constant is actually defined as the ratio between force and length. A better way to understand spring constant is to think of it as take the force and divide by the length, and now you know what the spring constant is. So that problem is more than just what's the force on those two. It's also how long is that going to stretch? Second thing is, this is 40 kilograms. What's wrong with just putting 40 here?
It's a mass unit, not a force unit.
Yeah. So remember, force equals mass times acceleration. So you actually have to take this times 9.81 for it to be a force in newtons. So remember, metric is a little more dangerous. You're being given a mass there of that box. Last problem was like 400 pounds. Oh, great, 400. This time 40 kilograms, not 40 kilograms. 40 times 10. This is like approaching 400 newtons down. So it's similar to the last problem, but it's not 3D. So I'm going to solve two equations, two unknowns here, not one equation, one unknown. Anyway, we'll have to talk about that later. We're out of time. All right, stay after if you want to talk about stuff. As usual, I apologize for going over, but I don't want you to be totally unprepared for your assignment.
Leah had like a question in the chat, so
Sweet. Let me pull it up. So Elias says, my auto isn't working great, but he has -8 instead of -80. Is that from, did I screw something up and not fix it, or did we catch it?
It's a really old comment.
That's an old one, yeah. I fixed that myself, I think. I didn't see her comment. But then she said, is it cheating on your homework to use Desmos? The answer is no. 3 equations, 3 unknowns without technology is very time consuming. So no, it isn't. And no, you don't have to show that to me. I'd like to know. In other words, I use Desmos to say Desmos, and then give me the answers that you got. And the same would be true on a test. But having said that, if you want to do the algebra, that's really good to do. I mean, it's really good to see if you're capable of doing it on your own, and then just kind of check your work. But you got to have time and so forth. And that's my style. I would far rather kind of make sure I actually understand. I like math. Math's kind of cool. And to be able to get things on myself and not have to rely on some machine to tell me the answers and so forth, that appeals to me too. So good for you, Leah. What else?
So do we have the let's see, both the 3.3 and 3.4 homework due on Tuesday?
Yes. Although if you get into a spring problem, I'd love to maybe start the day off with a little spring discussion on Tuesday. And so if you find yourself needing to finish a question in that homework assignment, great. I really don't intend for you to just say, oh, we ran out of time, go teach yourself, we're moving on. But obviously if we spend too much time on springs on Tuesday, then we're going to fall behind the same thing next week. So I'll try to figure out how much time we can spend on that. Fortunately, the following week, when we get into chapter 5, we only have one thing to cover, 5.4, and we have sort of 2 days to do it. But that's not because it's challenging that it's going to take 2 days. So. But I think you'll be able to get through a lot of your assignment based on what we just did.
Thank you.
I'm gonna answer Evel's question about number 5 on the test now. If anybody wants to see that. Wow, it's a big file. It's taking a while to download. Let me see. Yeah, I kind of need the picture, so I was just going to give up and start drawing it on separate paper, but I sort of need the picture. But in preparation for that, just got kicked out of my own meeting. That's not cool. So since this is primarily your question, Evold, I'm pulling up the note sheet.
I'll probably go. Bye, everybody.
Sounds good. See you, Ben. So you tell me, Evold, are you still there, Evold?
Oh, yeah, I'm here.
How good do you feel about that last note? Because question 5 is asking for the moment of a force about an axis. And so that about an axis. So I don't really know what your problem was on this. Was it, I don't understand how to kind of carry this out? Was it, oh, I didn't even realize that's the formula I was supposed to be looking at? I mean, like, enlighten me a little bit so I can help you in a way.
Yeah, I mean, the time was running out, and because I looked through the whole, like, all test really quick, and I saw I can do all of it, but just not this question right away.
Sure.
So I saved it to last because I don't want to use all the brain power for, you know,
Yeah,
that question. And after when I got to it, I'm like, wait a second. And I figure out that I supposed to use the, the formula number 6, the cheat sheet,
Okay.
but it was a little bit too late. And I just didn't know what is my next step after that.
Got it. So I got your test pulled up now. So before I get rid of these notes, then notice what we're asking for here. We're saying the unit vector length for the axis A. In other words, so how long is the axis? And the reason it's a unit vector is we don't really care how long it is. We just care what direction it points. We just need to know something about its direction. And we want it as a unit vector because the unit vector has a hypotenuse of 1. So when we do our multiplying, we're not changing the size of anything. All that's doing, that U vector is doing, is getting it oriented the right direction. So that's kind of tricky. And then these other parts are the same. So R is how far is it from a point on your axis from axis A to a point on the force vector. So how far is the force away from the axis? And then the last components are, what is the force itself? So what's the force itself? How far is it from the axis? What defines what direction the axis goes? That's kind of what U is. So let's take a look at that. I want to copy. I want to delete. What is this? Why can't I write on it? I wrote this. I should be able to erase it. Why can't I erase it? Oh well, just right on the top of it. So let's see, what did you do to get started on this? So you made the axis a little too complicated. Do you agree, Evel, that the axis here is right along the z-axis? Like it's not in a very confusing direction, if you will?
Yep.
So because of that, if I went from say O toward A, I could think of it as going up 1 in the y direction 0 and in the x direction 0. And you know, the z could be 7 or anything else. I mean, it's like, how long is that axis right there? I don't really care how long it is. But that's the direction it's going, 0 in the x, 0 in the y, and then something in the z. Does that make sense?
Yep.
But if we leave that as 7, then we're going to be multiplying by 7, and we're going to get 7 times too much rotation. So we need the Pythagorean theorem using 0, 0, and that number to be 1. And so I meant this to be easy on you in the sense that if you make that 1, then you're just multiplying by 1. And so that's the unit vector. That's u. So it's 0, 0, 1. Then the second part of this is, how far is it from that axis, actual lengths? How far is it from that axis to the force vector? And the reason those are actual lengths is because, well, isn't moment a force times the distance? Like, this is not a unit vector, it's actually distance. In other words, if it's 8 meters away, I need to know that because that's going to make a lot more rotation. So I got two choices. I could either go clear down here from O and go all the way from O to B. Notice I know where I am if I'm at B. Notice you don't know where you are at this tip down here. There, I don't know where that is. So I can go from O to B, or I could save myself a little time and go from A to B. So I only have to go, you know, over here and over there. So that second row, the R, is how far is this force vector away from the axis? Well, it's negative 12 in the x direction, since it's going that direction. Notice it's from A to B. It's how far is it from the axis to the force, not from the force to the axis. So it's negative 12 in the x direction, it's positive 8 in the y direction, and it's nothing in the z direction. Or you could say, well, no, if I went from O to A, it would be 6 in the z direction. It actually doesn't matter. Those are your two choices. Do you agree with that, Evel? Do you feel good about that?
Yeah, actually now it's pretty easy.
And then unfortunately, I need the X, Y, Z components of this 820 Newton force. And I don't have the X, Y, Z components. So I've got to make them myself from these dimensions. And so since I'm told this thing is aiming 4 meters in the X direction, 3 meters in the Y, and 5 down, then I can figure it out based on that. So again, if I do Pythagorean theorem, I get 3 squared plus 4 squared, that's 16 plus 9 plus 25. Which is 50, the square root of 50 is approximately 7.07. So this hypotenuse distance is 7.07. And so like we've been doing a lot, that's how I get my proportions. So as far as the force, its components would be 4 over 7.07 in the x direction. And again, notice that's positive, so that is positive. And then 3, which is also positive in the y direction. And then 5 is actually negative, so that'd be 5 down in the z direction. And if that's multiplied by that 820, then that's how I get that broken up into its components. So if you take 820 times 4 over 7.07, you get about 464. So that's how much of that 820 is going in the x direction. And you get about 348 in the y direction. And then z is going down. So 820 times negative 5 over 7.01, that's about 580. This is the matrix that if you take the determinant of, will take care of all of those complicated moments in 3 dimensions automatically for you. What do you think?
Yeah, I mean, just the first part got me a little bit confused.
Yeah, frankly, it was actually, I was trying to make the rotational axis simple by just making it vertical, but that kind of makes it worse because you kind of feel like you don't know what to do. If I had given you some axis that pointed off in some weird direction and I told you, you know, it's this far in x and that far in y and this far in z, then it's a little, you're doing more work to actually get those radius, the axis length numbers, if you will. Keep going. Who else has questions?
Okay, thank you, Doug. I'll see you next week.
Okay. Sounds good. See you all. I'm out of here. Hope you all have a good day. Goodbye, Leah.